All right. Welcome, everybody. It's my pleasure to introduce to you today Andreas Rauh. Andreas completed his diploma work at the University of TU München in electrical engineering and information technology, and then he went on to do his PhD work in control at the University of Ulm, and more recently has completed his habilitation at the University of Rostock. He has been very active in the area of set-based computation and has been involved in some of the most exciting work in this area, in my humble opinion. Currently, he's an assistant professor at the University of Rostock. And today, he will give us an introduction to some very interesting work that he has done in this area. So, without further ado, welcome, Andreas.
Okay, thanks a lot, Walid, for the kind introduction. And my plans for the day is to give you an overview of, let's say, a novel computational technique that allows us to simulate in a verified manner state enclosures for dynamical systems with uncertainty. And the uncertainty for those dynamical systems, they will be included, first of all, in the initial states of the system, and they can also represent, for example, bounded disturbances acting on the system dynamics, and also structural uncertainty, like, for example, uncertain but bounded parameters. Now, what you already see in the title of the presentation, I'll talk about exponential enclosure techniques, and that means using some exponential functions, we try to describe contracting enclosures of state trajectories, more or less for finite dimensional ODE systems over some specific time horizon. Now, let's have a look at the contents of the presentation. First of all, I want to motivate where these computational techniques are included. And they're included in a research activity that is called Valencia IVP. And Valencia stands for Validating Enclosures for Dynamical Systems Using Interval Arithmetic. And this IVP here just means initial value problems. And that's a work that I started around, I'm not sure, maybe 15 years ago, together with my colleague Katja Auer, who is now professor at the University of Wismar, close to Rostock. And as we developed this as a computationally efficient alternative to Taylor series and Taylor model-based simulation techniques. And what I will talk about in this presentation is, first of all, the fundamental enclosure technique, corresponding iteration scheme, and how to extend this, as it already was mentioned in the title of the presentation, how to extend it to these computational efficient exponential enclosures. Now, one of the key parts will be to decouple as far as possible the state equations from each other in order to avoid the well-known wrapping effect from interval arithmetic. And what you will see is, when we manage to counteract this wrapping effect, we'll manage to get tight enclosures for dynamical systems, which are characterized on the one hand by some non-oscillating behavior, and also on the other hand by oscillating behavior. And for the latter case, we will use complex valued interval arithmetic in order to describe the solution tubes here by a transformed set of state equations, which will be more or less represent using complex value state variables the corresponding system dynamics. Yes, and at the end you will see one or two smaller application scenarios. One is related also to a test rig that we have at the University of Rostock, where you can see the computational efficiency and the benefits of this approach. Now, let's have a look. What we want to investigate is an initial value problem for a set of ordinary differential equations. And in these ordinary differential equations, x is the corresponding state vector. We assume that the right-hand side is typically a nonlinear function of f. And what I want to restrict myself to in this talk is it's a smooth right-hand side. That means we can at least once continuously differentiate the right-hand side of the system now. Now, the initial conditions of the system, they are equal to this description that you see here. And this underlined variable represents the lower interval bound, the overlined variable, the upper interval bound, representing the infima and suprema of the knowledge about the initial state. Okay, what this would mean, for example, in a two-dimensional system model, that's just a rectangle that is describing all possible combinations of initial conditions here for our dynamical system under consideration. And this is what you see here, and this component-wise definition of the interval vector for each point of time. We assume that this is a proper interval. That means the lower bound is strictly less or equal than the corresponding interval. Now, what you see on the right-hand side of our set of differential equations is just a dependency on the state vector x. This comprises the system model, also closed-loop control strategies, in such a way that we already have predefined a controller. That means an input of a dynamical system represented by the ball-phase variable u, and this depends itself on the state vector, maybe on some parameters, and maybe also on some external reference signals. These are directly substituted into the right-hand side of the open loop plan, and in such a way we end up with this set of differential equations more or less in this autonomous dynamics. And corresponding uncertain system parameters, they can very easily be included in this state space representation just by assuming that they are uncertain but time invariant. That means just the corresponding time derivative of the parameter is equal to 0. Just plug them in as an extended entry in the state vector, and in such a way we can directly deal with uncertain parameters there as well. Now, the fundamental idea of Valencia IVP that we developed is try to find some approximate solution x tilde, and the corresponding interval bound x that encloses all reachable states at a given point of time t is then represented in such a way that we have this approximate solution plus some verified bound for the corresponding approximation error. This approximation error, this is usually calculated by a very simple iteration scheme, which can be derived, for example, using the PK iteration approach, and in such a way you end up with an interval x that contains all reachable states at some given point of time t after the initial point of time with absolute certainty. But the major problem of this definition, what you already see there, is you are adding an interval to an approximate solution, and this may lead to the problem of this growing uncertainty over time. The corresponding solution tubes, they may blow up. Okay, and this is certainly not feasible for cases, for example, where you know that the closed loop system model that I just talked about is asymptotically stable. If our system model is asymptotically stable, we expect that the corresponding solution tubes, that they remain bounded in their corresponding interval diameters, and they should contract. For example, if you have a well-defined equilibrium of the system, they should contract to the corresponding equilibrium state. And that's something that we want is to solve using the corresponding exponential enclosure technique that I will talk about in a few seconds on this next slide, one slide further. Now, what are the other alternatives that you could use for verified simulation there, which I'm skipping completely in this presentation? These are, for example, Taylor series-based approaches where you try to develop the solution of your set of ordinary differential equations. The differential equation, as I just mentioned, was x dot is equal to some as f of x, and the corresponding solution would be developed then as some initial point plus corresponding information about the time derivative plus information about the second time derivative, and so on. And usually what you have to do with, in order to enclose time discretization errors, if you want to enclose also information about uncertain initial conditions, you have to add some error interval. This E will be an error interval that depends on the integration step size that you take into account. And this captures round-off errors on the one hand, and on the other hand, it also captures influence of the corresponding truncation of this series after finite number of terms here. Okay, what you also see there is there are expressions, for example, this x dot, this x double dot. These corresponding terms here, they are multiplied with the corresponding integration step size, that means here t and t squared. And what you see, if you would perform an infinite series expansion, this would more or less be the exact solution of the ordinary differential equation. But for computational purposes, you have to cut it off. And this procedure is well known from literature. To use this also for interval arithmetic applications. For example, work of Rudolf Lohner, who worked at the University of Karlsruhe in Germany on that subject. There's work of Ned Medialkov, who did this in Canada. And one of his solvers is, for example, V-Node LP. And I compared one of the simulations using the corresponding exponential enclosure techniques that I'm presenting here with his solver in order to show you that the very simple iteration scheme that I'm deriving here is competitive with more complicated schemes. And the problem here of these schemes is that usually is in case that you have strongly nonlinear, highly coupled differential equations, the computational effort will become high. And yes, that's one thing that you want to counteract, especially in the cases where you want to use such guaranteed state enclosures here within a closed loop control strategy. Yes, and the idea to use such guaranteed enclosures in a closed loop control strategy would be, for example, to predict worst case bounds, let's say of a temperature of a dynamical system, and if your controller, let it be a predictive controller, has to make sure that you don't violate upper or lower bounds of the corresponding states, okay, you need verified information about the reachable states that can be obtained at some future point of time. And that's the reason why we want to get a computational cheap, but maybe less accurate solution. Less accurate in this case means the corresponding intervals still include the corresponding true states, but maybe they're slightly wider than the results that you would obtain, for example, with such a Taylor series-based approach. Now, if you want to get some further information about the basic iteration scheme, I just give you a hint here to a publication. It's a German publication here in Reliable Computing from 2012. And we presented it at one of the SCAN conferences, as one of the biggest interval arithmetic meetings taking place every second year. Now, what is the basic idea of the exponential enclosure technique? Let's assume that we have an asymptotically stable system. Let's say some x dot is equal to a times x, where a is strictly negative. You can easily determine the corresponding solution just in explicit form. The corresponding solution is nothing else than x of t is equal to e to the at times x at the initial point, 0. Okay, if you take into account uncertainty in the initial states, what do you have to do? Okay, let's evaluate the right-hand side in interval arithmetic. And what will hold now is, on the right-hand side you have an interval expression. This interval expression is guaranteed to contain all reasonable states at all future points of time t that are greater than 0. Okay, now what is this a? The a is nothing else than the eigenvalue. And this is more or less the motivation for this iteration scheme that you see on this slide. Let's assume, first of all, that we have an asymptotically stable linear system model where the state equations are fully decoupled. Let's assume that the dimension of the state vector is n. Okay, what we need is all state equations are completely decoupled. The corresponding eigenvalues should be placed on the diagonal of some matrix. This matrix is a matrix capital lambda. And you just evaluate the matrix exponential of lambda times t multiplied with the uncertainty in the corresponding initial state. And this leads to a guaranteed enclosure of the reachable states for all future points of time. Okay, here on the right-hand side, I just assumed that all the differential equations were fully decoupled. Okay, that's not practical in many real-life applications. For that reason, we will interpret this parameter matrix lambda at the end as some over-approximation of coupled system models in terms of a description of tubes that were assumed to be decoupled. Now, let's have a further look here. The matrix lambda is an interval matrix. Okay, in the decoupled case, this would mean nothing else than uncertainty of the eigenvalue. For example, from a system identification, we just know a lower and upper bound of the time constant of the system model. And this would be reflected here in the corresponding interval entry. Okay, in my iteration scheme, it does not also only account for the uncertainty of system parameters, but it also accounts for, as more or less interval variables that come from the iterative solution of the corresponding solution technique. Now, let's have a look how to derive this. What is well known is that you can use a fixed point iteration, the corresponding BK iteration, in order to enclose the solution of a set of ordinary differential equations if you know guaranteed bounds for the corresponding initial states, and if you have predefined some integration time horizon. Okay, One way how you could write this is this integral formulation. x0 is the corresponding interval box of the initial states. And on the right-hand side here is what you have to do is you have to integrate over the flow described by the right-hand side of the set of differential equations and plug in into the argument of the function f the corresponding state enclosure. Okay, now this is a hen and egg problem. What do you have? On the right-hand side, you don't know the corresponding interval enclosure that you have to plug in, and on the left-hand side, you also don't know. Under some assumptions, you can show that this will converge in an iterative manner. The iteration variable will be the superscript kappa here, and if you're initializing this variable here, this interval variable, in an appropriate manner, you will find some, at least, rough bounding box that encloses the corresponding states. And this idea will now be used in the following to express time-dependent expressions here for the state enclosures in a very simple manner. The simple manner is just going back to the previous slide, use this definition and plug it into the BK iteration and try to find now a corresponding iteration scheme that allows you to determine the corresponding interval entries that are included in the matrix lambda. And structurally, I have assumed that this corresponding matrix is a purely diagonal matrix. Now, what to do with this? Okay, the exact solution will be enclosed, as I just assumed here in the case of convergence, by this corresponding term here, the matrix exponential, evaluated for the new iteration step kappa plus 1, depending on the initial condition. And on the right-hand side, you're evaluating the corresponding expression, again under the assumption that this iteration is converging. You're evaluating this for the old iteration step. Okay, what is still troubling me a little bit is this integration over time. Okay, if this holds for the solution, it definitely holds also for the time derivative of the solution. That means we differentiate these two lines here with respect to time and end up with this corresponding description. What you see there is, over the time interval from 0 to capital T, that's the end of the discretization horizon that we take into account, we have now found the corresponding interval enclosure that contains all possible time derivatives depending here on the initial states. And those interval enclosures depend on the parameters lambda at the kappa plus first iteration step, while on the right-hand side, this corresponding expression is evaluated over the same time interval for the old parameter values at the iteration step. Okay, that's still a hen and egg problem. The problem is still on the left-hand side, you have this multiplicative coupling of the parameters lambda and some exponential function here. And it's impossible more or less to solve this corresponding expression for the parameters at the new iteration step. Okay, what I previously mentioned is I'm only interested in cases in which the iteration is guaranteed to converge. Okay, let's make the left-hand side a little bit larger. Making it larger means assume that your iteration is converging. That means the new result for the parameters that I'm searching for are a guaranteed subset of the parameters at the old iteration step. Where do we plug them in? Yes, we'll plug them in here for the parameters lambda in the exponential function. Okay, and now you can try to solve it. And since you enlarged the interval diameters on the left-hand side, I've definitely not lost a solution. Now we resolve the corresponding equation for the parameter lambda at the kappa plus first iteration step. Just for dividing here by this exponential term multiplied by the initial condition. Okay, there you have to be careful. You have to divide by an interval variable. Okay, division by 0 will be very harmful. Okay, when does division by 0 occur? It only occurs here for t equal to infinity. Okay, that's no problem at all. And it occurs in the case that the value 0 is included in the initial states. Okay, that's also not really critical, because in the case that 0 is the equilibrium and it is included in the initial state, okay, we know the solution. Okay, x equal to 0 will be the solution for all points of time. Okay, that's one thing we can easily exclude. And in such a way, we end up with the resulting iteration formula. The right-hand side was the original ith line of the corresponding nonlinear function. of the right-hand side of our set of ODEs, divided by the corresponding exponential term, and for the argument of the right-hand side of the function f, we have substituted the corresponding exponential enclosure. Okay, now the check is this corresponding parameter interval lambda a subset of the thing that we plugged in onto the right-hand side? If yes, we can continue the iteration. If no, we have to enlarge the corresponding intervals here, for example, by building the convex hull over the input and the output intervals, and try to search for parameter intervals lambda that are convergent. Okay, now let's assume that we simplify the right-hand side of our ordinary differential equations a little bit. Let's assume that they're just a pure linear combination of state variables. Okay, what does this mean? Because that means x dot is equal to a times x. Okay, if a dot is equal to a times x, that's linear dynamics. And what you see then, the function f that you had seen on the previous slide, they can be substituted with the corresponding coefficients here of our system matrix A. They can be substituted here into the numerator of this iteration formula. Okay, before evaluating it using interval arithmetic, you can even cancel out common terms in numerator and denominator, and the corresponding common terms are related to the diagonal entry of the matrix. Okay, let's assume that matrix A was completely diagonal. The result of this iteration formula is the diagonal element. Okay, that's just reading out of the matrix the corresponding eigenvalue. Okay, that means that's a consistent solution that is included in here. In all other cases where the off-diagonal elements are non-zero, this iteration formula leads to something. You're describing the solution tubes by decoupled tubes, and the corresponding coupling terms are represented here on the right-hand side by enlarging the corresponding interval diameters in such a way that the solution tubes contain the corresponding actual dynamics. As I already mentioned, the system is completely decoupled if the matrix A is only diagonal. What does this mean? That's free of overestimation, except for rounded errors. Okay, now what to do in practice? Okay, you could perform a simple preconditioning. A simple preconditioning, assuming that a system matrix with the entries Aij has only real eigenvalues. You can transform it into a diagonally dominant form, using, for example, the matrix of eigenvectors, or this transformation matrix, and then perform the corresponding iteration for the preconditioned system model. And the resulting solution has to be transformed backwards. Okay, this is what I mentioned here. Transform it into the real valued Jordan canonical form, and that's under the assumption that we have pairwise different eigenvalues, the best choice that you can do. Now, there are two things. How to initialize this iteration. Okay, my suggestion is find a suitable guess for the parameters lambda. As I already mentioned, we're transforming the set of state equations into a diagonally dominant form. Okay, we have a rough knowledge about the eigenvalues, at least of a point-valued approximation of this right-hand side of the system matrix. Okay, if the original system model was nonlinear, linearize it, compute the corresponding Jacobian of the right-hand side of the system model, determine in classical floating point arithmetic the corresponding eigenvalues, enlarge them a little bit, and this will be a suitable initialization for the parameter system. That's not too far away from the actual solution. Okay, now the other thing is, what is happening in cases that you have complex eigenvalues? Okay, how does the Jordan canonical form look like? If you take the real value Jordan canonical form, you have something like the real part sigma here on the diagonal of the transform system matrix, and on the off-diagonal elements, the eigenfrequency one times both positive and the other one times both negative sign. That's more or less this transformation that you have. Okay, that means you have two coupled equations. Okay, this still leads to a wrapping effect. In cases where the real parts are significantly larger than the imaginary parts, corresponding as absolute values are the things that I'm considering here. In the case that the absolute values of the real parts are much larger than the absolute values of the imaginary parts, this will also converge to a quite reasonable solution. Okay, this was the diagonally dominant form. Okay, but in cases where you have strong oscillations, where the omega is large compared to sigma, what should we do then? Okay, we could follow the same idea just by transforming the corresponding set of state equations into a complex valued state space representation and try to apply the corresponding iteration scheme to determine complex valued enclosures for these parameters lambda that you had seen there on the previous slide. Okay, and this is what you will see on this slide. The complex valued transformation will now turn the corresponding state vector, the original state vector x at the point of time equal to 0, which was a real valued interval box, into a complex valued interval box. And the corresponding, in case of perfectly null eigenvalues, the corresponding system matrix will then be fully decoupled, but the entries are the conjugate complex eigenvalue pairs. Okay, you end up with a full decoupling of this set of state equations in case that you have complex eigenvalues of multiplicity equal to 1. Okay, after this example, what you see here is the application number 1. I'll head on to multiple eigenvalues. That means multiplicity is larger than 1. There you have to make a few tricks in order to reduce the pessimism that this approach is introduced. Now, let's have a look. When is this complex valued iteration scheme applicable? Okay, you're dividing by the actual state enclosure for the ith state variable or for the I plus first state variable. Okay, the ith and the I plus first state variable, they just differ with respect to the sign here of the imaginary part. That means they're the corresponding conjugate complex solutions. Okay, when do I divide by 0 by the complex number? Okay, I just divide by 0 if the corresponding absolute value, or the square of the absolute value, includes the interval equal to 0. Okay, that's a product of two terms taking the absolute value. Okay, this product of the exponential functions, that's definitely not equal to 0. The only thing that can become 0 is the expression here depending on the initial state. Okay, if the transformed initial state includes the value 0, the iteration scheme is not applicable. Okay, but that's the same argument as I started with. If I start with the equilibrium, okay, I don't have to perform the iteration anymore, because then I know the true solution. Okay, that's not a really critical thing. That's only one thing you have to check in advance in order not to divide by 0 in the corresponding software implementation. Now, we have to keep in mind is we have a non-negligible wrapping effect in cases that you have multiple eigenvalues. This equally holds for cases that you have multiple real eigenvalues or multiple conjugate complex eigenvalue pairs. In both cases, you will get a wrapping effect, which I try to at least partially counteract after the following application scenario. And what we have to keep in mind is this transformation. We have an initial domain of uncertain states. This is now being transformed either into the real valued Jordan canonical form or into the complex valued Jordan canonical form. This initial transformation leads to some overestimation. Let's just take a box, rotate it, distort it a little bit. Okay, and you start the simulation with a rotated and distorted box, enclosed again by an axis-aligned box, or maybe midpoint radius representation by some disk in the complex plane. But this definitely leads to some overestimation, but usually this is not critical. This is the only thing that you will see afterwards in the application scenario, which turns my solution technique here slightly worse than the more computational demanding solutions based on the temporary Taylor series extension. And concerning a simple application scenario, that's one of the test rigs that we have at our chair at the University of Rostock. What you see on the right-hand side, we have a carriage that can be moved in horizontal direction via a linear drive and mounted in vertically upright direction here. On this carriage, we have a double beam structure. On this double beam structure, this aluminum box here, this cage can be moved in vertical upright and downward direction. And what this mimics is more or less a rack feeder system, where you, for example, have high bay storages. And this payload here included in the cage would be transported from one position to the next in some high bay shelf. And since such systems are usually built in a lightweight structure, Yes, you're exciting by the motion of the system, by a rapid motion, you're exciting structural vibrations. And the aim of a feedback controller there is to counteract such structural vibrations. In my verified simulation now, I try to predict the worst case influence of the oscillations here in terms of the worst case deflection here of the double beam structure. And what we take into account here is also temporarily varying locations here of the cage position. That means the eigenvalues of the corresponding beam structure here, they depend on the position of the cage itself. Okay, the question is how to derive a suitable mathematical model for this. Okay, what you have is more or less an elastical multi-body model. You have two lump masses. One is the mass here at the endpoint. This consists in the test rig here of a pulley through which the belt is here guided, the belt that is moving the cage in vertical upright direction. And we have the cage itself. These are 2 point masses. And the beam itself is just the double beams are moved together, more or less as a first physical model. Okay, they're described now by Bernoulli beams, by a single Bernoulli beam. And for this Bernoulli beam, we take into account with V1 and V2 the corresponding first and second eigenmode of the corresponding oscillation. Ys is the corresponding position of the foot point of the carriage. And the control input will either be the desired velocity of the carriage using an underlying current control loop or velocity control loop implemented directly on the electric drive for the horizontal motion, or it could also be the force if you use a torque control operating mode for the drive. Now, system parameters there are, for example, mass densities, cross-section areas of the beam. These are, for example, Young's modulus of the material that you account for. That means all of these parameters are not perfectly known in practice. They have some underlying manufacturing tolerances. Also, the material is not perfectly aluminium that you have here. Okay, that means each of the parameters will be interval quantities, and also the vertical location here of this payload of the cage is also not perfectly known. That leads to a further interval quantity here included in a linear state space representation of this dynamic system. Now, as I already mentioned, the system model is linear in this case, but it is uncertain. There are uncertainty, and in this case, in the case that your cage position is constant, you have a linear, uncertain, time invariant system model, or in the case that the cage is moving in upright, vertically upright and downward position due to the coupling with the corresponding parameter kappa. You can either say the system model is nonlinear because of nonlinear couplings between the state vector and the parameter kappa, or the other thing is you could say, okay, it actually resembles a linear dynamics, but with time varying characteristics. And in this case, you just assume that you can measure the actual position in vertical direction for the cage. Okay, altogether, in both of these cases, we have a system of 6 ordinary differential equations which are strongly coupled, and there exist 2 complex eigenvalues pairs of multiplicity equal to 1. Okay, the remaining 2 eigenvalues, they are real valued because they describe the horizontal motion for the carriage. And this was enforced by the underlying control strategy that the corresponding eigenvalues become real. Now, since we performed a suitable robust control design that covers all the possible realizations of kappa, we definitely know that the corresponding closed-loop system dynamics is asymptotically stable. That means we want to apply now the corresponding iteration scheme that I used before. I preconditioned the corresponding state equations just with the initial value for the parameter kappa, which described the vertical cage position. This corresponding state equations were preconditioned, and now on this slide you see there's one of the corresponding state variables, and this state variable x5 is the corresponding bending velocity for the first eigenmode here that is shown, and the corresponding bending velocity in meters per second is bounded from above and from below by the corresponding black solid lines here, and the corresponding blue dashed line represents the interval diameter, which is decaying over time. That means this system model, this is an autonomous system model after introducing here the corresponding feedback control loop, is being simulated in an asymptotically stable manner where the wrapping effect doesn't play any significant role. Okay, how does other software perform, for example? If I perform the direct evaluation of such a Taylor series ratio-based approach using, for example, Net-Medialkov's V0LP, I end up with a similar behavior. Okay, you see the interval diameters are slightly tighter. Okay, why? Yes, that's more or less only the initial uncertainty here. The initial uncertainty that was introduced by rotating the state box into a new coordinate system, but this is being attenuated afterwards. And yes, if you want to verify, for example, that your corresponding bending velocity doesn't exceed some predefined bounds, for example, safety critical predefined bounds, you end up with the corresponding left-hand simulation, maybe in a much faster way than with the corresponding simulation on the right-hand side. Okay, the implementation was a pure MATLAB implementation in this case, not optimized with respect to the computational speed, and I just made use of representing complex valued intervals in the corresponding midpoint radius form that is provided, for example, by the toolbox. As here on this slide, you can see there's a difference. Here was, the difference is just the blue box here. It's just a hint that more or less graphically you cannot distinguish the results between the case where you just treat kappa as a time invariant but uncertain parameter and where you take into account the vertical motion here of kappa, that means the payload position in vertical upward direction. Okay, the only thing that you have to keep in mind is if you want to simulate also the motion for the vertical cage position, you need a suitable step-size control strategy, since the corresponding feedback controller is implemented in such a way that the vertical motion is being controlled by an eigenvalue that is 1 order of magnitude larger than the corresponding motion in the horizontal direction. That means this has to be taken into account, and this can be done by selecting sufficiently small integration step sizes. Okay, they can easily be derived from the corresponding eigenvalues of the system model, and just take, 1 over the corresponding eigenvalue, take the absolute value, divide this, let's say, by 5, and that's a suitable integration step size. Okay, more details about the underlying control strategy that was implemented, about the modeling of this system, and also about the comparison with V0LP. This will be beyond the scope of this presentation today. This was published in 2013 at this control engineering conference here in Halmstad. Now, there's one question still open. In the case that you have eigenvalues of a higher multiplicity. Okay, in fact, you could treat the corresponding equations still as independent as I did before. Try to find cubes that enclose the corresponding system line. Okay, as I mentioned, you will suffer from the wrapping effect. Okay, what is the suitable way how to evaluate these equations? If you have a look there, the last line of the system model is completely decoupled. Okay, please do not start with the first equation and try to run the iteration, because then you get a wrapping effect that is influencing the parameters lambda that is propagating through the iteration. Okay, do it in a bottom-top manner. Okay, there, the last entry, this can be enclosed very easily, and the roughest enclosure will be obtained here for the first entry. Okay, that means always if you have eigenvalues that are either due to physical reasoning exactly of higher multiplicity, or for which due to uncertainty the eigenvalues domains overlap, start to integrate this in a bottom to top manner, and this will reduce the wrapping. That's one thing I always advertise here for. Okay. What do we have to do in the complex values thing? Okay, first of all, the same. The corresponding Jordan blocks here of higher multiplicity, what they have is they have the corresponding positive sign and negative signs of the imaginary parts, the ones above the diagonal. Okay, start the iteration again with the last line and evaluate them in a bottom to top manner. Okay, what you see on this slide is the definition here, the multiplicity of the eigenvalue should be delta I. And that's one thing that I want to make use now in an extended representation. In the case that your eigenvalue has a higher multiplicity than 1, you can also write up the complete exact solution. Okay, the completely exact solution would be something like this. It's for the ith state variable. The ith state variable corresponds to the first line here in this matrix. And the parameter j just iterates from 0 to delta minus 1. Delta minus 1 is the last state variable corresponding to the last line of this delta times delta Jordan. Okay, this is the corresponding exact solution in the case that you have a fully decoupled, perfectly known set of ordinary differential equations that is linear with higher eigenvalue multiplicity. Okay, first of all, when does this serve as an exponential enclosure? Okay, if we don't divide by 0. Okay, that's the same reasoning as before. Looks a little bit more complicated. Only divide by 0 in the case that this term here on the right hand side becomes equal to 0. And this can only happen if the value 0 is included here in the true solution set. Okay. Now, let's take this solution and try to figure out if we now assume that the parameters here in each of these lines here, the parameters for this eigenvalues, sigma I plus j omega I, that these eigenvalue enclosures are more or less, first of all, treated as independent for each of the lines. And let's see if we find an iteration scheme for that. Okay, let's play the same trick. Assume this as the corresponding solution. Differentiate it with respect to time. Okay, differentiating it with respect to time leads to terms. Okay, that's just the product rule of differentiation that I have to apply here. First of all, the sum, depending on the time variable t, has to be differentiated, and the exponential function has to be differentiated separately. Okay, these are the two lines. I started with differentiating the exponential function, and the second line here is differentiating the big round brackets. Okay, now what we can do is we plug those expressions into the original iteration scheme. After assuming that our iteration scheme is converging, that means this term here with the exponential function is expressed in terms of the result of the previous iteration step. This term here on the left-hand side leads to the corresponding outcome of the kappa plus first iteration. We can resolve the corresponding expressions here for the corresponding kappa lambda values at the kappa plus first iteration step. Okay, this is what you see on this slide. Our subsystem model into which we substituted these expressions is just this one-sided coupled structure. The first line depends on the second, and so on. And as I already mentioned, try to find the solutions in the bottom to top. Yeah. After doing so, we end up with these iteration formulas. Yes, they're an extended version of what we had before. And what you will see afterwards, for some, this will be an academic example. This completely counteracts also for simple system models, helps to counteract the corresponding wrapping effect that takes place. Okay, now with this expression, what you see is the parameter lambda I star here. This is what I call the true eigenvalue. This can be an uncertain parameter, no problem at all. Just replace it by the corresponding interval variable. We are evaluating this again over some finitely long time horizon from 0 to capital T. Okay, if we want to continue from T to something else, okay, perform a shift in time, also no problem at all. And after some symbolic simplifications, we end up with this T. And in the case that the eigenvalue multiplicity was equal to 0, you see that's the original solution. Now, we have a practical important case. The practical important case is that you have some joint coupling, these red expressions here, acting jointly on each of these lines in the Jordan block. They can be state dependencies, they can be input dependencies, they can be disturbances acting jointly on these equations. Okay, then you have, with these additional red terms here on the right hand side, you have a coupling that you cannot neglect anymore. And in this case, the advertisement that I meant before, integrate from bottom to top, doesn't work anymore. Okay, in this case, you have to perform a vector-valued iteration. What does it mean, a vector-valued iteration? Okay, you have to check the enclosure property simultaneously for each row of these column vectors. Okay, but that's the only thing that you have to change. And the other thing that you have to change is, okay, add here the corresponding term in the numerator, the corresponding red term, this fi that you had here on the right-hand side, that represents the joint coupling terms. Okay, in cases, and that's a practically very important case, in case that the maximum eigenvalue multiplicity is equal to 2, okay, these expressions simplify to what you see on the slide here. Yeah, that's more or less obvious what is happening there. And this simplification was also the thing that I implemented 2 slides further on in the academic applications. Now, plugging them in, you end up with the corresponding simplified solution. And there I have to point out one thing additionally. I don't know if you recognized it in the first part of the presentation. There are products and quotients of exponential functions where the exponent of these expressions, you have the unknown parameter lambda, this interval variable. Okay, how to implement those terms here in a computationally efficient form if you have A in the numerator as the exponent, B in the denominator. Try to reduce the dependency problem in such a way that you symbolically reformulate those expressions. Okay, this is what I wrote here. In each of these terms, these are such quotients, a symbolic reformulation of the right-hand side, but this holds always. This can be implemented, can be coded in a hard fashion in the corresponding MATLAB or C code or wherever. And that's a simplification that you definitely have to keep in mind in order to get rid of unnecessary multiple interval dependencies, which may lead to a blow up of enclosures that can easily be avoided in this case. Okay, now let's have a look at an uncertain system model. This uncertain system model was described here by these eigenvalues. That's in fact a fourth order system model. These eigenvalues are conjugate complex, and the corresponding midpoints here, these are the things that you see here on the left hand side before the comma here. We have a negative real part -2. The midpoint has the imaginary part +3, and we have a disk here of radius 0.1 around this eigenvalue. Okay, that's the first. Here we have the corresponding second eigenvalue, and each of them has the multiplicity equal to 2. Okay, our corresponding initial states, they are also described here in the midpoint radius notation. It's just arbitrarily chosen here. A value -5 and -4, again with an interval diameter of 0.1. You could choose arbitrary values there. And what you see is the initial information leads firstly to a widening of the state enclosure. And after some time, the corresponding iteration scheme leads to a contraction of the solution tube. And this solution tube contains directly what you have seen here on the right-hand side. These expressions lambda derived from the corresponding iterations. Okay, this holds for all of these state variables. I just picked out the real and imaginary parts of the corresponding complex valued state enclosures for the first and the second state variables. Okay, I could go on with number 3 and 4. Okay, they were decoupled. Okay, not really interesting. And at the end, the only thing that is missing there, this result has to be transformed back into the corresponding original set of coordinates. Okay, how is this being done? This is also being done in a very simple way. If Z of t is defined by some transformation matrix multiplied by the corresponding original state vector, okay, what you have to do is the corresponding interval enclosure x of t that you have is the inverse of this matrix. Okay, the forward and backward transformation does have to exist, multiplied by the complex valued interval enclosure at each point of time t, and from that only the real part still think that makes sense. That's the solution enclosure. Okay. Without the wrapping effect for point value solution, this is actually real valued on the right-hand side. Everything that is complex valued results from overestimation from the wrapping effect in the backward transformation. This can be cut off. Okay, this already leads me to a summary of the presentation and to a short outlook to what you will hear in tomorrow's seminar. First of all, what you have seen is a computationally efficient, very simple iteration scheme to describe system models or corresponding state enclosures for dynamic system models, where the linear dynamics have the dominant effect. Okay, we had assumed that the corresponding dynamic system is asymptotically stable. Okay, that's usually by design. When I'm a control engineer, my goal is to design an asymptotically stable controller. That means if my controller is asymptotically stable, that's a simulation-based verification stage of the design. That means it makes sense to search for the corresponding contracting enclosures. Okay, and extensions here, and there's still room for further work here, have been already firstly implemented here for multiple collinear complex eigenvalues. Now, the range of applications where you can use this is very wide. What you could do is you can verify, maybe even in real time, the corresponding worst case lower and upper bounds for state variables. This can be done, for example, in safety analysis of some control strategy. For example, if you detect a violation of a state constraint, you could switch the system off or bring it to a safe state. What you could do is you can include it in a predictive control strategy. You could use online sensitivity analysis. You can perform state or parameter identification on the basis of these guaranteed enclosures. You can analyze feedback linearizing controllers. You can use this in what are also implemented in the last few years, interval-based sliding mode control procedures or backstepping controllers. Yes, in this case, the control law depends on the uncertainty of the predicted states, which has to be defuzzified at the end. Okay, and the final thing that is not written here on this slide is something for which I have to advertise for Julia's presentation tomorrow, because you can also perform further simplifications by transforming these sets of state equations into a more or less dynamical system model that follows specific monotonicity properties in the initial states, where you can derive lower and upper bounding systems simultaneously, which allow you to perform point value simulations in the case that you trust your floating point arithmetic, or in the case that you want to capture a round of errors or time discretization errors. Okay, we take Julia's bounding systems and evaluate them using this corresponding exponential enclosure techniques. Then we have even treated the corresponding time discretization errors in a verified manner. We have treated the round of errors in a verified manner using the interval arithmetic. Okay, the only thing that we have to trust in is the library for interval arithmetic is correct. Okay, from that point of view, I would like to thank you for your attention, and I have just selected two of the publications. I think the second one is the one which I already transferred to at least two persons here in the audience. And yes, I'm now open for questions. Please feel free to ask. Thanks for your attention.
Thank you very much, Andreas, for a great presentation. Questions from the audience?
How did you sort of prove formally that this, when you have a contracting system, that state vectors converge to each other, how did you sort of prove that you can do this kind of, it's not a linearization, but that you can use a linear system to approximate, to get this bound to this nonlinear system? I mean, everything was really nice with this presentation. The only gap for me was actually how did you show this step where you went from the nonlinear system to
that's one thing that you will find in, don't let me lie, in which paper it was published fully. It was published in the SCAM 2012 paper that is cited there. It was published in this journal article. And the idea behind this is using the PK iteration.
Yeah.
And yes, the only thing that is assumed there is that Banner's fixed point theorem has to hold. And under these assumptions, you can formally prove that that's a correct iteration scheme. There's nothing else than a slight generalization of the classical Picard iteration, because in the classic Picard iteration, you would assume this as a constant bound and would perform the fixed point iteration. And in this case, it's just plugging in a time varying bound, and you have to show that this holds for all points of time over this integration interval. That's the only generalization.
So this is an excellent question. And I was also very interested in this because that's one of the things that we would like to do with your method. Your point about Picard is really interesting because I think Picard is very central in the study of these systems because it works very well when you generalize to sets. It seems that it just generalizes very naturally to sets. One thing that maybe may happen here is this is conditioned on the convergence of the iteration. And the tricky part is your choice of representation, such as your choice of assumptions about the form of the enclosure, such as being a decoupled linear system, could prevent you from converging for some systems. So as long as there's some convergence that happens from some initial states, then we know that we can we have that connection.
Yes,
thank you for clarifying.
Yes, and there's also a further extension which makes use, let's say, of, that's not my extension, but for example, the Taylor model-based integrators, like for example, they're implemented in Riot or Cozy UI. What they're using is they're using a higher order polynomial expression plus an interval remainder term. Yes, and they also developed some iteration scheme for the parameter of this polynomial expression. And this is also based, it's not directly based on Banach's fixed point theorem, but it's based on Schauder theorem. They have very strong links to each other. There's a small marginal differences between them. And the thing that was also done there is developing an iteration scheme which is very close to this expression here. And yes, this leads to a much more complicated shape. And yes, as you already mentioned, it depends on representing the uncertainty. Okay, you could also use ellipsoids, for example, to represent the uncertainty. You could use some sonotopes, for example, parallel epipets or whatever. And for each of these basic shapes, it is possible to derive such iteration expressions that allow you to describe the corresponding solution sets. Yes, and a further extension that I'm, for example, currently working on is using these iterations also for the case that you have fractional order differential equations. And yes, there was quite recently, I think 2 or 3 years ago, a publication where it was shown that the Picard iteration directly generalizes also to fractional order systems.
Yeah, I'm not looking so much on fractional order.
Yes, but you can directly copy these expressions here to the fractional case. The only thing that you have to exchange is this matrix exponential has to be replaced by the corresponding method Leffler function. And that's it.
I mean, in this Jordan form, when you have multiplicity, eigenvalue multiplicity larger than 1, so you get these ones in the diagonal, like the first. You get some kind of polynomial solutions, right? And this is, but this was not the problem here, right? I only saw exponential.
But the polynomials are here.
Yeah, sorry, they're there. Yeah, now I see them. Obviously, up to delta minus 1, so that makes sense. Yeah.
Maybe you'll find a misprint on this slide.
No, this looks exactly what I want to see.
Secular terms.
Yeah. Sorry.
Yes, the only thing that becomes tricky there is how to find the transformation into the Jordan canonical form, because what you may need there is not only the eigenvectors, but maybe some corresponding generalizations that lead to the corresponding eigendecompositions.
Exactly, yes.
But in the case that you have independent eigenvectors still, it's easy.
Yes.
So I have a small question. for general nonlinear systems, it's quite possible that one of these convergence steps, if we require the diagonal form, that we don't have a fixed point, or at least a fixed point that we find quickly. Or it might be that we just find that the over approximation is quite big. Mm. Is there a kind of a convenient way, let's say, by controlling, by going from diagonal, let's say, to certain forms of Jordan forms, so that we can, kind of turn a knob maybe in an automatic way to see if this doesn't work together?
Yes, it's really hard to answer. Okay. Because the hard thing that you mentioned is a general nonlinear system. What is general?
Yeah.
Or how general?
Yeah.
The thing is, what will work is if you have a system model that you can rewrite, also like we went to tomorrow, in such a way that you have your nonlinear expression. You're rewriting it in such a way, exactly by factoring out the state vector, that you have a state-dependent matrix A of X, and this state dependency could be treated purely formally as a time-varying uncertain parameter. In such a way, you're over-approximating the nonlinear dynamics by more or less a polytopic uncertainty model. And this is what Julia is doing tomorrow in one of her presentations, not in one of her presentations. Yes, in fact, it's joining the results of 2 papers. This is why I was a little bit confused. But the thing is, if you're doing it in such a way, then you could try to at least the corresponding midpoint matrix could be diagonalized.
Yeah.
Okay, and you could hope that the state dependency is not so critical that also evaluating the matrix for the complete range of reasonable states will also lead to something suitably conditioned for the iteration.
Okay. Yeah. It's very good to know that this is kind of the most natural way or a sensible way to go forward.
Yes, and there's one further thing. Since I'm an engineer, I know where my state equations come from. And usually you know that, for example, some conservation properties hold. Okay, let's assume this is, for example, a fluidic system. You have represented the corresponding dynamics by a compartment model. Fluid flow going from one compartment to the next one. Okay, this has to be continuous. You won't lose anything except for the case that you have some leakage in between. But you have the continuity of mass. You have the corresponding continuity of the corresponding mass flow in between. Okay, what you could do is you could sum up, for example, let's say the I plus first and ith state equation. You could derive some new additional, or let's say redundant state variables in such a way in order to check which part of the state enclosures results from overestimation, from the wrapping effect, from multiple interval dependencies, just by checking if the corresponding expressions violate some, let's say, energy constraint, if they violate, for example, mass constraints or whatever. And usually such constraints, they can just be, by summing up over those terms here, they can just be derived by summing up the right-hand sides of the state equations. And that's internal energy of the thermal systems or mass balances.
What about if you would extend this with some additional controller, for example, constant, so that your system is not on this form, like it's not maybe an autonomous system, or would you be able to look at these kind of things a bit?
Currently, I just assume that the controller is already known.
Yeah.
Okay. This is what is showed here.
Yeah, exactly. It's basically a feedback controller. So
yeah, the feedback controller plugged in.
Yeah.
Okay. If it's an open loop controller, for example, you have piecewise constant inputs.
Exactly.
Okay, that's the same. Also, no problem at all.
Okay.
The interesting thing is if the control structure is still to be optimized. What to do then? And yes, currently, as we're trying to develop, this will be for hopefully published paper in the very near future. We're currently in the final stages of deriving, let's say, some kind of iteration scheme. An iteration scheme for computing the controller gain matrix included in this expression in an iterative fashion. by an underlying simulation, let's call it reachability analysis, using, for example, this exponential enclosure technique. And the idea will be to find a robust controller game that always points inwards to a domain of reachable states, a domain of attraction. And in such a way, you could design, for example, either a constant controller game that is valid for some finite time duration, or you could even develop some kind of game scheduling approaches. We have, say, for example, in domains where you have large variations of state variables, to split up the time interval into short time spans, determine a constant gain for the short time interval. We have small variations of the states. Okay, we can live also with a constant gain for a longer time period. And it's a very interesting thing, but that's still under current investigation. Hopefully we'll have something in the very near future for that.
Awesome. Any other questions from the audience? I have maybe one small question. In the red terms, where we had the disturbances, were these functions of t? I am curious about whether. So as I would have expected, the disturbances would be a function of t. Now, of course, here we're talking about.
They're very simple. They can be functions of t.
They can be functions of t. So the FIs, they can be implicitly functions of t in this case?
This trick, right?
Just use this trick. Include that time as a state variable.
Yeah. Got it. All right. Very good.
Yeah.
Perfect.
Yes.
Yes.
Okay, this is not asymptotically stable, but you know the eigenvalue. The eigenvalue is decoupled from the rest. It's exactly equal to 1.
Perfect.
Linear root elite rowing.
You actually said that in your paper in one sentence. All of it. You know, you could put the input and the disturbances in one.
Yeah. Yes, I think it was written.
And then I saw it here.
Parameters and time as extended state variables.
Yeah. This is perfect.
Yes, and from that point of view, you can treat dynamic controllers, for example, PD or PID controllers. You could include observer structures, which have their own integrators inside.
Yep.
You could integrate backstepping controllers, where you have some integrators inside into the same formal formalism. And the time dependency.
So you include P also as state verb. Yes.
And there I just have P dot equal to 0.
Yeah.
Or in the case that I know some temporal variation rates are bounded parameters, it will be an interval on the right-hand side for the variation rate. I think that's the easiest trick how to handle that.
It's really awesome because when you put on, these remarks are great, when you put on your computer science hat, you worry about a lot of these things. And for some reason, even for me, that I've actually seen these observations, ideas before, you need to think explicitly about this whole set of tricks, like you say, to make it. I appreciate the simple form of the,
yes, but I think that's the interconnection between someone coming from mathematics, a computer scientist, a control engineer. Yes, me as a control engineer, I'm familiar with the modeling and I know what to expect that the system is doing. Okay, and from that reasoning, such tricks are more or less obvious.
Yeah, absolutely.
Okay, but from a mathematical point of view, for example, let's discuss about why is this converging. Yes, that's the thing we have to keep in mind, that we don't lose some parts of the solution, but just a too sloppy formulation, for example, of the problem.
Any other questions? Andreas, thank you very much for an awesome talk.
Okay, and thanks for having me.